The title, I stress, if you look, I stress this second quantization many-body dispersion formalism towards modeling million atoms. I want to stress these two words because I will not present results from million atom systems. Of course, if not, if I would present them, the whole purpose of this long program would not be there. The problem would be solved, in other words. So it's towards in the sense that what I present today is a series of methods that I think could be of some help to address this problem. Let's get into what is the challenge. The problem that can be formulated in a very, very general way is starting from Schrödinger equations, describing in general the quantum level of the atomic scale, included the description of nuclei, undistinguishable electrons, coupled towards them all these objects, all these entities, towards Coulomb electrostatic interactions, in first approximation, of course, because all of them, the real object which mediates the interaction is the electromagnetic field. But on the scale we are considering generally in quantum chemistry, the Coulomb potential is fine. And what we would like to observe is how from this quantum microscopic work, extended objects at the nano up to micrometric scale, to including objects of the size much larger than 10 to the 5 atoms, so the 1 million atoms problem, emerge and are structured and organized. And this is the problem that we face, for instance, in molecular crystal or in very complicated biomolecular complex. So the idea is how from this world, that world emerge. And as Martin brilliantly described before, the atomistic perspective, so try just to put together our information on the microscopic level and transport on the macroscopic level is not probably the right strategy, because these two worlds manifest very qualitative different properties. So how I gave my contribution in this field? Let's start from the general picture, because there are many possible ways to attack this problem. One is the DFT perspective that many of you know much better than me. So already at this level, there are some simplifications that have been done, because the nuclei generally, for my knowledge, are considered fixed geometry and boundary conditions, and one wants to describe the electronic degrees of freedom through a density function and satisfying the minimization for a given functional, that is the constant functional, that provides the potential, eventually, when solved and evaluated in the solution for the right function, provided the solution for the interaction energy among the nuclei. Among all the terms that compose this functional, the kinetic energy functional, the electrostatic interaction between the nuclei and the electrons, the mean field interaction among the electronic density, and exchange correlation functional, what I'm interested in and what I will focus my attention for all the talk is just a small part of this functional, the exchange correlation energy functional, and in particular the parts that take into account for the correlation among quantum electronic fluctuation beyond the mean field approximation. So this is a very limited and small part of the problem sim. We are in a limited perspective, and from this limited perspective, I take one single term, and of this single term I just consider a small fraction. But as Martin showed before, this part is really relevant when one wants to understand and comprehend, which is the emergence of organization on large scale, given the large scale, the nano and micrometric scale we referred before. Moreover, I would like to add a few examples where probably, inspired by experiment, nature, and observation, that tells us that the understanding of the behavior of this electronic, the correlation among the electronic quantum fluctuation is really important. One of them is the breaking operated by a restriction enzyme, echo R1 on the DNA in a brilliant paper written by Philip Kurian and collaborators. It has been showed. It has been provided an explanation of a strange phenomena. When the restriction enzyme acts on the DNA, the breaks take place in 2 points in a synchronous way. It's very rare to find a cut just in one place. And how to obtain a synchronous cutting on 2 sides distance of 25 angstrom with something more than back-on-the-envelope calculation, but less of the complexity with respect to the full DFT problem, Philip and collaborators evaluate that probably there's a resonance between the energy, the collective energy modes of some quantum electronic fluctuations associated to the nucleotides on the DNA and the energy required to break the phosphodiester bonds in the DNA. So this is an indication that maybe the energy and the amounts of the dynamics of these electronic quantum fluctuation eventually transfer at the level of the nuclei and can cause this kind of problem, of situation of great interest, suggesting the possibility that quantum electronic fluctuation mediate a new pathway for allostery in complex biomolecules. Another really experimental field where I was involved also, where the role of this quantum electronic fluctuation seems important to explain the behavior of intermolecular interactions, is the one where this is experiment I participated as the theoretical interpreter of what was happening in Marseille and Montpellier and Rome. It was a big collaboration. And what we have observed in this experiment is that proteins marked with a fluorochrome and pumped with visible light as an increase, manifested this enormous amplification in the absorption of Terence frequency. So you pump energy in the optics where light, and we obtain an increase in the absorption in Terence. And we interpret this as the effect of pumping collective modes inside the protein. Now, despite there are 2 aspects that are important to be stressed in this problem. That is something astonishing. Even consider that when we pumped, these are recent paper published on Science Advanced, when we used this protein of the algae, this fluorescent protein contained in the algae, pumped with the same method, we observed that beyond a certain threshold, there's a clustering transition, both augmenting so we consider a solution of this biomolecule. We pumped it then with this visible radiation, and what we observed is that the diffusion coefficient dropped as a function of the concentration, meaning that, and this concentration is such that the intermolecular average distance is in the order of 1,000 angstrom. So the idea is that through this terahertz collective mode, giant dipole oscillation have been activated that plays a role in organizing the dynamics of this biomolecule at the distance of 1,000 angstrom, which is considerably large. Why electronic fluctuation? For 2 reasons. First, in order to explain how this collective excitation takes place eventually in biomolecules, because we have force field methods and there are ongoing work trying to understand the origin of this enhancement of the absorption coefficient in biomolecule due to the external pumping. So the generation of this collective giant dipole fluctuation, but the usual force field based on pairwise interaction are not able at the moment, it seems, to fully represent what happens. So maybe there's a role, at the intramolecular level played by electronic correlation fluctuation, correlation among electronic fluctuation in order to generate long-range force field that can help to explain where these large dipole oscillation come from. And on the other side, we have estimated that the dipole momentum, the dynamical dipole momentum of these objects, this pumped biomolecule, is in the order of 1,000 of the Bis. And where it's come from? Probably there's a coordination due to water layer around, but in order to understand how water molecule organize around the protein, we need the methods that Martin described before, probably. And so the pathway mediated by correlation among electronic fluctuation is one possible explanation for this coordination. So to address all this problem seems really, really fundamental and important to understand better the nature of these quantum electronic fluctuations. As Martin brilliantly described before, so I don't want to spend too much time on this. This quantum electronic fluctuation can be, and their contribution to in terms of energy, of correlation energy, can be fully understood in terms of the adiabatic connection fluctuation dissipation theorem, where the fundamental object is this polarizability tensor field coming from the solution of some Dyson equation, where this A0 polarizability field is derived by the solution and the response of the field, calculating, assuming as exact the mean field solution of the Conchamp functional. The interaction has been described before, are coupled through this tensor. This is a rank 2 tensor, which depends both on the Coulomb interaction and on this exchange correlation function that is in principle unknown or very complicated, however, to estimate. So one of the hypotheses, the RPA hypothesis, is to ignore the contribution to this tensor and operate a range separation into short-range interaction that are treated self-consistently and reabsorbed somewhat in the definition of the polarizability tensor field, and a long-range part which correlate far atoms. Moreover, this polarizability tensor field is reprojected on an atomic basis, so that now we have a discrete representation, a localization of this tensor field. So we have tensor dots, a system of tensor dots. The response of this system of tensor dots, it has been, in RPA approximation, it has been proved to be equal to one of a system of coupled Drude oscillator. As Alexander told the first day in his tutorial, Drude oscillator, quantum harmonic oscillator carrying a dipole moment through a positive charge in a fixed center, let's say, and the negative charge which is oscillating around it. The coupling between the harmonic oscillator has been assumed to be dipole-dipole Coulomb coupling, so this is a linear quadratic Hamiltonian, and here it starts my interest. This is my starting point. Sorry for this long introduction, but it was just to understand why this Hamiltonian is important and why now I will focus just on that model. Because I really assume in what is the following of my presentation that this quantum Drude Hamiltonian model is a viable representation for the correlation among of the electronic fluctuation around the mean field solution, and so can give some insight. Of course, it is possible to solve and diagonalize this simple problem, to diagonalize this Hamiltonian and to find eigen frequencies and eigenmodes in this first quantization formalism, very important. So we map displacement of this Drude oscillator in collective displacement, which is the meaning is less clear for this collective variable. The MBD energy, so the contribution to the functional given by this model, is just the difference between the ground state of the interacting and the non-interacting system.
Matteo, how are the boundary conditions specified?
Which boundary condition? That one?
Yeah, I mean, the geometry is clear. Yes, those.
The boundary condition, I refer first of all to the solution of your original DFT problem. That's one point. And the second point is the form of the potential that you put here. Of course, if you have an infinite open system, you will have a form of the Coulomb potential. If you have boundaries, it will take a different form. However, the prescription to derive this tensor, given your scalar potential, was given to slide before. It's fine? Yeah. So this model is relevant, and let's say at the beginning, this model was conceived just to provide an effective way to calculate this number, the energy, and some quantities related to it, like the force field or the polarizability that are immediately connected to it. So it was just an effective model that allows to calculate number with efficiency and accuracy. But then it reveals that maybe there is more physics inside this model. In other words, it's more than just a tool to calculate easily and accurately scalar quantities like energy. And the point is that probably some important information on the degrees of freedom of the system of this electronic fluctuation is contained in this harmonic oscillator representation. This is evident in a paper that is recently published by Alberto Ambrosetti, collaborators, and Alexandre Kachenko, where two main facts have been proved. The MBD spectrum is correlated with the optical spectrum calculated with the Bethe-Salpeter method. So there's a good qualitative agreement in the shape, even if in order to obtain a superposition, you need to shift slightly these two spectra. And the excited state can qualitatively change the MBD interaction. So if we take a system like these two benzene, and we suppose that we are able to excite an MBD mode, the interaction energy between the object in the system, the MBD interaction energy I've defined before change, and also the dependence from the distance between the object, and consequently, also the dynamics eventually of a force field derived by that. So these are two messages. One is that it's not only a matter of ground state. Even excited state in this model and excited state in an Hamiltonian system are associated to the dynamics. So even excited state could provide interesting information. They're more just than minimization of a functional, just in brackets, of course. And there could be some very important physical insights on the possibility to control the dispersive interaction acting on the excitation of these collective electronic correlation modes. On the other side, this method, due to its efficiency and accuracy in describing large systems, has been used in order to investigate the contribution of interaction energy in large systems, and I don't want to enter too much into the detail because Martin provided a beautiful picture before. What I just want to stress is that through this method, it was possible for the first time to observe how this dispersive interaction plays a role in connecting different length scale in our system, for instance, because the range of electronic correlation in the solvated protein system described before by Martin has been found up to 20 angstrom. And preliminary results on the EQR1 DNA model I have described before found that the interaction energy between two sites far apart, 23 angstrom are 25 larger with respect in MBD picture with respect to the classical Energy-Jones potential approach. And also there's these many-body dispersive modes affect the dynamics at this, and consider that these modes for the parametrization of the Drude oscillator generally lives into the, as a characteristic frequency in the order of petahertz. So we are in a UV. And so the characteristic scale of the ground state energy of a single Drude oscillator is in the order of electron volts, while but it has been observed that this electronic fluctuation can generate low-frequency phononic collective modes. So through the forces generated by this field, there's the possibility to connect what happens at the scale of electron volts to the scale of low-frequency phononic modes, typically in the scale of centi-electron volts. So we say that these phenomena are really important because they act as a bridge between two very different scales: the electronic local scale of electronic localized fluctuation on the electron, and on the other side, on the full molecular or intramolecular even scale. And the magic is operated by considering the long-rangeness of the electromagnetic field, which is behind the scene all the time, but is the real player that helps to synchronize all these objects. So why don't address is an efficient and accurate method? Why don't put 1 million atom system directly into the machine and find numbers? Also because there are many questions that are connected to the possibility to solve this problem. One is the role played by the MBD interactions in describing the dynamic of this complex large system, and the other is how collective modes couple with external degrees of freedom, because for the moment, as I described before, everything is with fixed nuclei, imagining that there's no environment around, but one would like to couple these MBD modes eventually both with phononic modes or an external electromagnetic field, for instance. As we have seen, excited MBD state can affect deeply the dynamics. So one would like to understand better this picture and find an answer to this question. Unfortunately, brutal force approach to the calculation and estimation of MBD interaction is not a possibility due to the high computational cost on the combined DFT plus MBD algorithm at the moment implemented. There are conceptual limitations then in describing, in using an atomistic model that wants aim to describe large systems, as Martin showed before. And moreover, think to this fact, the characteristic frequency of one of these Drude oscillators or their collective modes range in the frequency range of petahertz. So if we transform it in a wavelength for light, for electromagnetic radiations, this means something around 20 nanometers. So as long as we start to approach 20 nanometer size, we should take into the account for retardation effect and decoupling with the background electromagnetic field. So the picture is not complete. We should take into the account a little bit of the dynamics of this mode and their coupling with the external electromagnetic field. So the solution seems to be develop a coarse-graining approach. The coarse-graining approach can be pursued through two possible pathways. One, as Martin mentioned before, more or less, one is partitioning smaller fragments weakly coupled among them our object. So let's say a protein, and consider a fragmentation and so operate a real space coarse-graining. I take my real space representation of the degrees of freedom, the protein, and I try to fragment it in different parts. Or another way and I just study the coupling between the fragments. Another possible way to operate a coarse-graining is to reduce the number of degrees of freedom, picking from a given system the more important or relevant MBD modes and couple them with the rest of the environment or with other degrees of freedom. And this is sort of non-local coarse-graining approach because what we consider are collective degrees of freedom coupled among them. Both these approaches present some challenges in this respect of the MBD model for quantum Drude oscillators. From the real space, we would like to be able to localize global MBD observable into a fragment basis set, so to reproject this MBD energy or any kind of global observable evaluated through this Hamiltonian to a fragment basis set. On the other side, we would like to quantify the correlation among the different fragments in order to understand if our fragmentation is optimal with respect to the problem of decouple the system. So having strongly correlated fragment inside, self-interacting very strongly, but weakly coupled between them. And on the other side, we would like to operate in order to operate the reduction of the degrees of freedom, we would be able to associate the coupling constant with the other degrees of freedom to each MBD mode in order to create a rank and pick the more important one for a given system in order to operate our reduction. Both these path and the challenges correlated required to easily read and decode the information contained in the MBD ground states. So to be able to pick and to connect the representation at the level of normal modes with the representation at the level of single atomic Drude oscillators. Actually, and that's the point I stressed at the beginning, is a second-quantization formalism. And in second-quantization, despite the possibility to visualize the displacement associated with its mode in a nice way, despite this, the global properties of the MBD ground states are difficult to reproject on the atomic basis. In other words, it's difficult to read here, at least from my perspective, which are the which is the state of a single atom or a single fragment, if I look at this in a way that is more maybe familiar to the language that has been of this community, I would like to express the MBD ground state in terms of the Drude oscillator orbitals in this decomposition, because I would like to be able to reproject and to understand the contribution of each Drude oscillator to this MBD ground state. So the issues of the first quantization formalism are, first of all, where are the quanta? Because we have not used the quantum nature fully and properly in the first quantization and in the actual formulation. We're just taking the only point where the quantumness enters into the problem is in the assumption that there exists a ground state energy whose difference is whose value for harmonic oscillator is 1/2 h bar omega. That's the whole part of quantumness. But there's no real quantum. We don't look at really quantum nature of this system of Drude oscillator. The same problem could be rephrased in a pure classical sense at the level of the diagonalization of the Hamiltonian, of course. On the other side, there's the interpretation issues I mentioned before. So one would like to express the MBD ground state in terms of these Drude oscillator single particle orbitals, in order to connect these two levels of the representation, the atomic and the collective one. Then in practice, one would face the problem to calculate expectation value of observable, even including excited state for the problem that we have seen before. And even if one want to consider the coupling with the external electromagnetic field. So for this reason, it would be nice to have an easy way to compute the value of observable evaluated among excited state, and using Hermite polynomials in this representation is quite complicated. Martin told me he tried it and he wrote 20 pages of integral for simple formulas. So one would like to have a nicer picture to calculate this expectation value. And the second point is that a strategical point. When we want to connect the degrees of, in quantum physics, in quantum system, is generally more useful to think about exchange of quanta of energy. That's the real, is connected with the first point. When we want to couple system, it's more efficient to see it in terms of exchange of quanta. And this helps to connect with the problem to study interaction of MBD modes with the environment. Environment be, for instance, a phononic lattice, a phononic a system, a set of phononic modes, and this could rise to a polarons represent. For instance, this connected strongly with the description of polarons. So this is the idea that I bring, the simple idea, it's just not even an idea, a change of perspective on this problem. Try to look at the problem of the connection between Drude oscillator and collective MBD modes associated to these plasmonic-like waves that represent the correlation among electronic quantum fluctuations in the second quantization representation. And let's see how this problem is rephrased at this level of second quantization. So in terms of excitation and creation annihilation operator for these modes. How, in other words, the algebra of creation annihilation operator for the single atomic oscillator is connected with the algebra of the collective modes. And this is made through the Bogolyubov transformation, which is a linear transformation, very well known in condensed matter physics. The interesting things of this Bogolyubov transformation is that these are they preserve the canonical quantum transformation. And in other words, they are the equivalent of symplectic transformation in the context of quantum system. The advantage of this that could appear just as a mathematical details is that this symplectic transformation admits a unitary representation that connects the coherent basis set, the state of the coherent state in the atomic basis set with the coherent state of the collective MBD modes, and is operated by the unitary transformation. And we see this is a simple example of two one-dimensional QDOs at a given distance. This is a representation of the first entries of the density matrix. When they are distant, they are both in the ground state, and when I approach them, I start to populate the excited state of the system. And here I have a mixture, what in quantum optics is called a squeezed state. So a mixing of excitation of both the oscillator that represent the ground state of the fully coupled system. So this is just the theoretical introduction. There are questions. It's clear why I'm doing what since here? Okay. Thank you. So let's start to see realistic systems, to apply all this machinery, this theoretical machinery to realistic system and to get some insights. For instance, I have applied to this sort of toy model of fullerene C70 ball surrounded by Fanning ring. And in this asymmetric geometry, we see that the occupation number of these carbons is higher with respect, for instance, to these carbons that are here in the Fanning ring, in this far region. And what does it mean? It means that these quantum Drude oscillators are really excited, we have populated the excited state, all the excited state of the quantum Drude oscillator. Bogolyubov transformation populate all the excited state at any order for the nature of the unitary transformation that I showed before. While for a more symmetric system, we see that we don't see we don't see in the ground state, in the population of the QDOs, in the atomic QDOs, the same kind of asymmetry. So this is a benchmark that my calculations were fine. This is the variance because why I plotted this variance of the QDO normalized, or well, the other way around, is the average value normalized with the variance. because I wanted to understand how far these systems are from the distribution of the occupation number for a single QDO, one-dimensional QDO, is far from being Poissonian. Because we know that for coherent state, for instance, another kind of transformation, the canonical transformation I showed in my tutorials, the distribution of the occupation number in each mode after you have operated your displacement operation is a Poissonian, and I wanted to check how strong is the Poissonian condition on each carbon atom. And we see that in the asymmetric case, there are much more, the distribution is much more spread. These are the degrees of freedom of the phenyl ring. These are the degrees of freedom of the balls. Of course, the balls being more interacting is more far from a Poissonian distribution, which is also the limit of the non-interacting case, because in this case you have a Poissonian completely collapsed to the zero case, while this distance from this discrepancy from the Poissonian behavior of the occupation number signals that the system here, for instance, in the ball, is much more strongly interacting than for the QDOs that are situated here. And the correlation are stronger. So for this reason, of course, I also plotted the correlations. The correlations that, of course, are stronger in the ball. This is the confirmation of what we have seen before at the level of single Drude oscillator. Here, at the level of coupled Drude oscillator, the mutual correlation are much higher in the ball with respect to the phenyl ring. And here, in these two blocks, we distinguish the effect of decoupling of the ball with the phenyl ring, and we see that different geometries creates different patterns in these regions.
Matteo, just a question. So the energy difference between the asymmetric top
there's no energy.
There's zero.
This is a covariance of occupation number. So
no. I understand on the right. I'm saying on the left.
On the left.
On the left. I just want to make sure. So we have a difference in maybe factor of 3 order of magnitude difference in the two. But what energy scale does that correspond to?
I will show you, because this is the level. It's just to say that, okay, now we are able to see the occupation number, something that before is a way to try to visualize how this MBD ground state is made. Because till now it was possible just to write, to draw arrows on atoms that represent a single mode, but we didn't have a picture of how it looks, the MBD ground state. And maybe it could be useful to look at correlations, at interactions, in order to connect these atomic and global level to see how is the anatomy of this MBD ground state.
And just so that I understand on the right, so the top ball is more strongly, it has a higher mean occupation number. Yes. But then you're saying that the bottom right is showing stronger correlations in the upper right quadrant. So
this one, no, depends. I mean,
the upper right quadrant of the bottom.
The upper right quadrant, this one.
That one.
This one is the ball. In both the case, this is the ball.
Yes.
This is ball ring, and this is the ring.
Okay.
So the ball is strongly, just what I wanted to say is just that the ball is much more strongly interacting and correlated. At this level, correlated. The correlation between occupation number in the ball are much higher than in the rest of. Okay. Of course, the following step is to reproject and calculate the energy. So to reproject the global EMBD energy on the system. And we see that for the atomistic Coarse-graining level, we found pictures that are really similar, really close to the one that we observed before, respectively for the atomic average occupation number in the ground state and the correlation among occupation number, in this case, that correlates with the interfragment MBD energy. So these are important because offers a picture of where the MBD energy, this is the self-MBD energy, which I want to point out here that on this atomic basis set is always positive. And this is a nice manifestation of the variational principle. So the MBD ground state does not minimize the energy for the single through the 3D through the oscillator localized on a single atom. And this is the reason why when I refer the energy of each atom to its ground state, here we see just positive values. It's a confirmation of the variational principle. So in this picture are the interaction, are the sum of these self-atomic MBD energy with the interaction energy. The interaction energy part, despite the single contribution, are much smaller than the self-atomic MBD energy. The sum, here we have n terms, we have n square, order n square terms. So at the end, the negative part provided by the interaction energy overcome over the positive excitation over the single atoms. And the interesting point was these two things to say. This matrix at this level provides just a map to reproject the MBD energy on atomic fragment basis, but more in general, this could be thought as a sort of localized MBD field and pairwise interaction between scalar potential effective between atoms. The interesting point is that if one machine learn this matrix, I will return on this point later, this could be the key to provide a description in terms of a pairwise potential that effectively encode all the information of the many-body dispersive interaction. Because, yes, here I have reprojected on couple the MBD energy. You see, here is the potential energy evaluated on the ground states, the interaction potential evaluated on the MBD ground state. So it seems that I have constructed a pairwise potential, but in fact, all the correlation at the many-body level are encoded through the expectation value on the MBD ground state. So it's a way to construct an effective pairwise potential that fully encode all the information of the many-body dispersive interactions. And more, one can think to an even further projection, an even further contraction of this energy, and think to sum over all the rows. This is an idea coming from many discussions with Martin, and construct an effective single atom potential that encode the information over all the n many-body interaction into the system. So it's a way to reproject in a canonical way, giving with a certain meaning sense. Is not, of course, the only possibility to reproject the energy, but this is one quite straightforward way to start from a scalar quantities associated to a system and to construct an atomic basis field that fully encode the n-body interaction among the different parts. And this could be pushed further, thinking to, in the respect of coarse-graining, thinking to a different way to fragment the system. So we can find a coarser representation of the system in the scale the ball with the Fenner rings, and repeat the same construction at this level. So this is the interesting part is that it's now possible at any level to construct a scalar field and a pairwise potential that fully encode the n-body behavior of the system. Of course, we see here, for instance, that in that representation, the self-energy of this fragment could be both positive and negative, especially for the sphere, which is highly self-interacting. Why? Because in this representation, I have taken into account into the self-energy of the fragment, even the interaction potential inside each fragment. So these are negative elements, and for sufficiently large system as the ball, it is sufficient to construct a negative self-fragment MBD energy. This is just for sake of completeness, the coarse representation of the ball with the ring. I mean, this is the other extreme. This is the other extreme between that is on the other side with respect to the atomic representation. So is not very useful then for purpose, but it's just to show the possibility that in principle one can construct these fields for any level of coarse graining. This possibility allows to investigate for changing, for instance, the geometry of the system, how the MBD energy is distributed in this system. And we see here, this I took as the reference state for the total MBD energy, the MBD energy at 20 angstrom. And I see how it changed the contribution due to the self-energy of the ball, the sum of all the self-energies of the Fenner rings, the mutual interactions between the Fenner rings, the mutual interaction between the ring and the ball, and the MBD energy. And what is interesting is that it is non-trivial, is not only the, as we noticed before, the positive value of the sum of the on-site Fenner ring. Probably they are, in this system, in this configuration, they are still sufficiently small such that the self-interaction cannot compensate the higher interaction excitation due to the fact that the single atoms are excited in the MBD ground state. So the energy is positive. But moreover, we see that, and this is interesting, yes, the interaction energy between the ball and the ring is negative, the total MBD energy is negative, but the interaction potential between the rings, the Fenner in the rings, is positive. So it means that the balls acts effectively as a repulsion in these rings. It's the destabilizing object in this ring. And this is, of course, this is the UC70 energy that is much higher here. So also the ring destabilizes the balls. This is the interesting part. The effect of the geometry, of this geometry with respect to this case where they are considerably asymptotically far, is that the ball is destabilized by the presence of the ring, and on the other side, so it's less compact, and on the other side, the interaction energies among the Fenner rings is slower, is weaker, because this, why you interpret this? Because this Fenner maximize to be very cohesive, to have a very cohesive force, have to be synchronized among them. But being a very polarizable object in the center of the system, they don't synchronize, they don't speak among them, they speak with the ball. And so they are not more efficient, not anymore sufficiently efficiently synchronized among them, the quantum electronic fluctuation. They are not correlated because they have to be correlated with a highly polarizable system in the middle. And so they mutually destabilized by the presence of the ball. This is one, maybe it's really trivial, but it's one example of the kind of diagnostic that can be performed through this reprojection method. And here is the evaluation on the scaling law on how the energy, the interaction energy between the ball and the single Fenner rings change with the distance. And I compare with the respect to the pairwise TS case. What is interesting is that if I take the logarithm of the ratio and evaluate it with respect to the logarithm of the distances, I obtain this k value, and this k value is essentially the difference between, if I assume that the coupling coefficient between the fragment and the ball are equivalent, so the C6 coefficient are the same both for TS interaction and MBD interaction, and effective, I construct an effective MBD potential of the form C MBD divided R to the 6 minus k, this is the k that appears in this formula. So it's the difference with respect to the behavior of the van der Waals pairwise potential. Higher the number, lower in absolute value the exponent at the denominator. And we see that is not a great deviation, but still is not 1 over R6, is 1 over R5.85 for some of the phenyl here. Of course, are the phenyl that are in the region which is more strongly interacting, the orange and the red one, that are more destabilized. The other here in this region far follows much more close the 1 over R6 pattern. Of course, this kind of diagnostic can be applied also to biomolecule to investigate how the MBD energy reproject on the different fragment basis. So here the self-energy for the residue basis, the interaction potential in the residue basis, and the reprojection, so the sum of these matrix where I re-included on the diagonal this contribution for this reprojected MBD energy. And also in this case, we can notice some nice things. For instance, there are also in that case some terms which are positive, completely positive, that here becomes completely negative. And this term, which is quite strongly interacting, quite strongly excited, but there are other much more excited here. In this picture, has these fragments is weakly coupled, probably. The residue here are weakly coupled with the rest of the protein in these terminals. When I resum all the interaction potential energy, the interaction potential energy in absolute value of this part is quite small. So I have to be negative, but due to the fact that it's weakly coupled with all the rest of the system, the residue here, yes, are negative, but not so much as, for instance, in the alpha helices with we expect strong correlation, and where the residues are much, much strongly correlated. This is more evident in the secondary structure reprojection.
That arrow should be upside down, right?
Yes, of course,
yeah,
of course.
Okay.
This is what I said before. These matrices, this matrix representation could be eventually used in machine learning programs and methods in order to infer and to construct effective potential and force field, because the same reprojection can be applied even to the force field and to eventually reproject which is the contribution of the force given by some other fragments. Could be an interesting point for developing coarse-graining methods in machine learning. To include, as this was one of the problems raised yesterday by Stefan, to include these long-range interactions into the force field, and this could be one possible strategy to do it. The second point was the calculation. Just for the sake of time, I will go fast. The same facility that we have to evaluate matrix element allows to calculate transition dipoles, so that now we can see and evaluate for a given mode, which is the contribution to the transition dipole here, for instance, along each axis for this system, for this toy model. This is a more symmetrical configuration. And we show that effectively the larger, this is something expected, but it's nice to see the values in the bi, is there's slightly difference between these arrows that gives the contribution of the displacement to an MBD mode with respect to these colors, which tell us, which take into account for the polarizability and the contribution to the polarization and to the collective dipole of each Drude oscillator. So here is contained much more information than here, and especially is contained the information on the contribution given by the effective charge carried and the polarizability carried by this single Drude oscillator.
What did you mean by IQ representation in the upper left? I cube?
First quantization representation
okay.
is that.
Okay.
The contribution of the single, so I can evaluate, as said before, the contribution of a single atom to a given MBD mode and reproject on the basis, for instance, I needed a scalar quantity to avoid to project too much arrows. And I decided to reproject these isotropic square transition dipoles. And the interesting thing is the possibility to calculate the transition dipole, so it's a sort of oscillator strength versus frequency of MBD modes for this protein. And analyzing this peak, one can reveal and reprojecting on the, let's say, residue basis, but it's an arbitrary choice, you can choose any kind of basis, one can obtain a map where these transition dipoles are higher and where smaller, both in absolute value and in being positive or negative. And this is what I think Martin before refers with polarizable and depolarizable, is the positive and negative contribution to this matrix whose summation, the sum of all entries gives you the total oscillator strength. That are terms that augment and increase the oscillator strength and other terms that decrease the complex oscillator strength. And what we notice here is the complete delocalization. We don't recognize any pattern. This is a very delocalized mode. On the contrary, I pick this very, very high frequency mode and I see that it's very localized, very few collective, and probably it's essentially related to a very localized interaction which is weakly coupled with the rest of the electromagnetic radiation. So this is interesting. Collective MBD modes with large dipoles, very localized MBD modes with a few not coupled. And in the perspective of the coarse-graining, these modes can, for instance, throw out. The last part, I go very quickly, is to say, okay, we have seen that I have the possibility to reproject scalar quantities on a fragment basis, but which is the most, there is an optimal way to choose a fragment basis. And from here, the idea to introduce quantum information methods into the arena of MBD modes description, because these are coupled Gaussian variables, continuous variables. The density matrix for this system can be written in this way. Of course, there's a problem, there's the issues about that is raised many times, but which is the interplay between MBD mode and temperature. At the level of just electronic degrees of freedom, ignoring the phononic degrees of freedom, there's no issues, because the MBD mode are in the range of electron volts, the gaps, and the thermal fluctuation are in the order of centi-electron volts, so we can ignore thermal fluctuation. The MBD density matrix is the pure state on the ground state. And we have a method to quantify how strongly two fragments are correlated, or better to say, the degrees of freedom belonging to each fragments are correlated, is the mutual information amongst the two fragments. The calculation of the mutual information require the calculation of the entropy on the density matrix. How to calculate the density matrix is, in principle, could be a very complicated problem, but given the fact that there's a Bogolyubov transformation which connects the non-interacting QDO system with the interacting QDO ground state, there's the QDO ground state is a Gaussian state, and Gaussian state has the strong advantage that are fully characterized by the covariance matrix that appears in the Wigner quasi-probability distribution. And through a procedure related to the Williamson theorem, it's possible to define a set of so-called symplectic eigenvalues that are nothing less than the eigenvalues of the correlation matrix that you have diagonalized through a symplectic matrix, not an orthogonal one. And this, for Gaussian state, is possible to write an equivalence between the entropy of a given system and the correlation matrix of the system or the subsystem. And this relation is established through this formula where these are the symplectic eigenvalues. So I did this, and I calculated the mutual information in the QDOS ground state for, in the MBD ground state for the protein we have seen before into the two different coarse-graining realization. And the point is that through this method, one has the possibility to characterize how strongly are connected the two systems. Now, this could be employed, for instance, for a self-detection of which are, with machine learning methods, for instance, that identify which is the optimal partition of the system, which minimize the mutual information among the different parts. Just this is a natural question, how this mutual information correlates with the distance, is scaled with 1 over R6 at least for the protein. And this is very nice. It has the exact same behavior of the potential MBD energy among the fragments. So this is a nice fact because it maybe is trivial, but it's nice to see that it's essentially the MBD potential, the strength of the MBD potential among the fragments that establish the correlation among the degrees of freedom. So I don't want to spend too much time into conclusion. Just the take-home message is we need a method to get more information on the MBD ground state to develop coarse-grain method that allows to exploit the full power of the MBD methods to investigate long-range dispersion interactions in large systems. To do this, the second quantization method seems to be a nice perspective that allows to increase the efficiency of and the easiness in calculating matrix element and observable in this system, and open the possibility to a diagnostic of the degrees of freedom of the correlated electrons system. Thank you very much for your attention.